your lines with a straight edge. Don't freehand it, please. Okay, so there's 3 rules. What I want to tell everybody is there's 3 rays you draw. Okay, number 1, the first ray you draw is what we call parallel in. Okay, this parallel in, and it goes through the focal point, coming out. Okay, so in other words, I draw parallel in means I draw this line parallel to the optic axis. Okay. Now, remember, if a line comes parallel into a spherical mirror, where does it will reflect? Where does it reflect? It reflects through the focal point. So it comes and it will reflect through this focal point. Okay, that's what we call ray number 1. And you always number your rays. Okay, number your rays. Okay, now notice that the ray comes in this direction, but it also we'll see if it appears like it comes from this direction. We shall see, maybe not. Okay, ray number 2. Ray number 2 is what we call parallel out. So you have to go through the focal point, then it's parallel out. So imagine this ray here went through the focal point. Remember, anything that goes through the focal point comes out parallel out. Okay, so we have another ray, and we send this ray through the focal point. And where does it come? It comes out parallel. Comes up parallel. That's ray number 2. So in other words, whenever you have a glass like this, an optic, the ray can always go backwards and forwards. So remember, imagine this ray were parallel in. Parallel in would reflect and come through the focal point, back to here. Okay, so we can always take these rays back and forth. Okay, 2 different ways. So ray number 1 is parallel in and reflects through the focal point. Ray number 2, it goes through the focal point, but it's parallel out. Parallel out. Okay. Then ray number 3, it goes let's see here. Ray number, well, I just made an error right here. Okay, ray number 3 goes through the radius. Okay. Ray number 3 goes through the radius. Now, if a ray goes through the radius, it reflects right back on itself. Ray number 3 goes through the radius, hits the mirror, and bounces right back. So it goes this way, but then it comes right back. Notice it went through the radius this time. Radius. For a lens, if you go through the radius, a ray that goes through the radius hits the mirror and it reflects right back through the radius. Okay? Because if you think about it, if you have a spherical mirror, if you send a ray out right from the radius, it will bounce right back onto itself. Okay? If that is the radius. Okay? So So where's the image is formed where all three rays merge. That's where the image is. So we start at the very top of this image, and this pointed tip is located right here. And we came off the optic axis, so it would be right here. Okay, so that would be the image. That's the image right down here. So notice that the image, is it real or if it's virtual? Now notice, do you have to go through the mirror to get to the image? In this case, no, you do not. No, you do not. So the image is okay. The image is real. The image is real. That is, if it's on this side of the mirror, if the image were on the opposite side of the mirror, it would be a virtual image. But it's not. It's on this side of the mirror, so it's a real image. It's inverted. Notice that it's going this way. It's upside down. And is it reduced or magnified? It's reduced. It is reduced. Okay? So notice how we draw, again, to reiterate for mirrors, that actually for lenses, we're going to have the exact same three rays, but for mirrors, we will say here are the three rays. The first one is parallel in. Again, just to repeat, the first ray is parallel in, and it bounces through the focal point, coming out. Ray number 2, here's ray number 2. It's parallel out, but to get it parallel out, it has to go through the focal point. Okay. And then the third ray goes right through the radius and comes right back on itself. And where these rays intersect, that's where the image, the top of the image is formed. Okay? So this is all by what we call ray tracing. We didn't need that line, turns out. This is called what we call ray tracing in optics. And this is kind of the old tried and true method of doing optics. And so it's good that they're actually teaching you to do this, called ray tracing, where you actually trace the rays. Okay? So that's that's on page 394. Now let's flip over and let's look at the example on 395. I'm going to erase this now. Okay, on page 395 we have another situation. In this case it's a concave mirror, but the object is inside the focal point. Okay, so we have here's our optic axis. We draw a concave mirror. Oh, that's not so good, but we'll let it go. And let's see, it's 7 centimeters. I'm going to make it 7 inches to the focus, and that would be another 7 to the radius. So here would be the radius. Okay? And the object is 5 here's the object. Okay. So again, we have a concave mirror. The object is inside the focal point. Okay. So again, let's go through our 3 rays. Ray number 1 is parallel in. Okay, the ray goes parallel in, and where does it go? If ray goes parallel into the mirror, it bounces and goes through the focal point. Remember, that's our go. And comes out. So this is number 1. Go through the focal point. And it comes through the focal point, and this will be ray number 1. Okay. We're on page 392 through 395, then flip to 396. Okay, the next one is parallel out. Whoops. And it goes through the focal point and then comes parallel out. So how do we go through the focal point? Well, we have to start at the focal point. Okay. We have to start at the focal point. I'm going to extend this up some. We have to start at the focal point, and it comes way up here, and we have to hit this. Okay, so this ray comes through the focal point. This is ray number 2. Hits the tip. We always are working with the tip, and then it comes parallel out. Okay, so that's ray number 2. Okay, I'm going to, so ray number 2 comes through the focal point, hits the tip, and parallel out. Okay? Does that make sense? Okay. Ray number 3 goes through, whoops, through the radius. Okay. Ray number 3 goes through the radius. So we start from the radius and go right to the tip. Goes through the radius, right to the mirror, and then it comes back on itself. So here's ray number 3. Start from the radius, goes through the tip, goes that way, but then it bounces back on itself. Okay, now the question is, where do all of these rays meet? Where did these rays converge? I'm going to switch pins here. Where all do these rays merge together? Well, they certainly don't. Look at ray number 1, ray number 2, and ray number 3 do not merge together on the left-hand side of the mirror. There's no way. In fact, they look like they're diverging. They are. They're actually going away. They're diverging. But could they meet on the other side of the mirror as virtual rays? And the only way to know is, in fact, they will. If this ray here is coming out, but it acts as if you're on this side of the mirror, that it's coming out straight. Okay? We're going to even extend that further. So this is what we call the virtual number 2. Ray number 2, if I look at this ray number 2, I should start with the 1 first, but I start number 2, it bounces and comes out, but when it comes out straight, if you're on this side, it looks as if this ray would extend back. Okay? That's the same thing. Let's do that to ray number 1. Ray number 1, okay, remember ray number 1 goes in this way, but it comes out this way. So where would it extend back to? if we take that ray and we extend it back, it would come back to here. So that's virtual ray number 1. Okay? Now notice you may say, well, what about going this way from ray number 1? Well, it's going into the bore this way, but it's when it's coming back out. In other words, if you're right here, looking here, you would say, well, the ray's coming at you. It looks as if it's coming from way back here. Now let's do the same thing for ray number 3. Ray number 3 goes right through the same radius, so it has to, and you can see where it's going to go. And if I drew this right, it will be pretty close. I'm a little bit off, but not too much. Okay, so ray number 3, this will be virtual ray number 3. Now, if I had drawn this exactly, these would all converge at a point. Well, they don't quite converge at a point, but you can see where they're wanting to converge right up here. So in other words, this tip right here is going to look like it's coming from right in here. So this is going to be the image. Notice that the image is a real virtual. It's a virtual image. It's a virtual image. Okay. It's upright. It's an upright image. It's going up. It's not flipped. And it's magnified. It's magnified. Okay. It's magnified. Now, you all, if you've played around with mirrors, you all know this effect very well. This is one of these, this is a mirror that used to belong to my wife, but I've confiscated it for physics. On the one side is simply a flat mirror, okay, but if I flip it around, it has a slight curvature to it, okay, curvature to it, and if you have one of these mirrors, if you look at yourself with the flat mirrors, you just see yourself. But if you flip it around, you look magnified. You look, if you look at this curved surface, you see your image way back here, but it magnifies you. Okay, your face looks bigger. Okay, so that's exactly what we have here. It's a virtual image. To get to the image is way back here, but it's magnified, and it's magnified definitely compared to if I flip it around and just had a flat mirror. All right. So, okay. So I hope that's clear. So using these techniques, you should be able to solve just about any mirror type of problem. Now we're going to flip over and do the same thing to lenses. Well, actually, no. Let's do one more. Let's flip over to page 398. And the book wants to do a convex problem. So that might be a good idea. The way to succeed in doing these optics problems, these ray tracing, is just to do lots of problems. There's no way you can solve these problems if you've never actually drawn them out. The only way to do it, to solve these problems, is practice, practice, practice. Do lots and lots of problems and actually draw them out, scale them out, draw them the best you can, be like you're a draftsman, and when you draw them out well, these problems will work. Okay. Excuse me, I need to take a drink of water. Okay, if you go to the 398 to 399, here we have a problem. Let's see, that is a convex problem. A convex mirror problem. Whoops. Okay, so here's our optic axis. this, oops. Let me draw that again. Here's our optic axis. It's a convex problem, convex mirror. So if we're on the left-hand side, generally optics problems are solved from the left to the right. So the object's on the left, image will be somewhere on the right. Here is a convex lens problem. So it bends like that. The object is 14 centimeters away, and I'm using 14 inches. So here's the object. It's 14 centimeters. Okay, the focal point is 5. Here's the focal length. That's 5 centimeters from the optic axis. Here's the optic axis. And the radius, of course, would be another 5, half that. Here's another 5 centimeters to the radius. Okay, so the question is, where's the image to this? Again, this is a convex. Whoops. Convex mirror. We always do our problems from the left to the right. Okay, again, do the exact same thing. Ray number 1 is parallel in. Okay. So we draw it parallel in. Here comes the ray. Now notice, because the mirror is convex, how is it going to reflect? If we draw normal here, it's going to reflect back. But it's going to reflect back as if it came through the focal point. Okay. It's going to reflect as if it came through this focal point. This is a virtual ray, of course, but the virtual ray will look like it came right through the focal point. So this is number 1. Number 1, parallel in, and it comes out through it comes out as if it came through the focal point right here. Hope that makes sense. That's ray number 1. Number 2 is through F, and then it's parallel out. Okay, how do we go through F? Well, through F, it would be okay. We're going to draw it as if it's going through F. Okay. In other words, in this kind of case, the focal point is on this side. It's on the right-hand side. But we draw it as if it is going through the focal point, but it never gets there because it comes out parallel. Whoops. Yes. Okay. That's ray number 2. So this appears like it went to the focal point, but it's actually coming parallel out. And notice, if I draw the virtual ray going back, it would come back like that. Okay? So we draw it as if it's going through the focal point, but it bounces back parallel out. So it has to be ray number 2 is parallel out. Okay? Ray number 3 is through the radius. Okay, now if we draw the ray as if it goes, here's the radius, so we have to draw it way as if it goes through the radius. Okay. It goes through the radius. Okay, and what happens? It actually bounces back, so it is drawn as if it's going to go through the radius, this point here. So this is a virtual ray. It's drawn as if it will go through the radius, but it bounces back on itself. So this is ray number 3. You have to draw these very finely. And where do all these 3 converge? These 3 converge right here. In this case, the virtual rays converge. Again, here's virtual ray number 1, here's virtual ray number 2, and here's virtual ray number 3. It's very close to virtual ray number 2. Number 2 and 3 look very similar. Okay? But so this image, it's virtual because it's on the opposite side of the mirror. You have to break through the mirror to get to the image. It's upright, pointed upright, and it's reduced. The size is reduced with regards to the image is smaller than the object, so it's reduced. Okay. Well, that's all the mirror problems we're going to solve right now. I hope that makes sense. Again, there'll be lots of practice problems on these also. Okay, on page 400, and let's see, 400, let's see here. Well, page 400 to 401, 402, 403, and 404, we're dealing here with what's called Snell's law and index of refraction. Let's first talk about, well, we'll just talk about it all together. What's called Snell's law and refraction, and we have to talk about also what's called the index of refraction. Whoops, I spelled that wrong. Index of refraction, which is given a symbol N. Okay. And this is on page 400. Now what happens is if we have a sheet of glass, let's say this is air, and this is glass, and this sheet of glass goes way suppose this is a thick sheet of glass down here, okay? And we shoot a laser beam, a ray, that's my dog right over there making noise. If we shoot a ray, a light ray, into here, we're going to draw the normal. The normal is perpendicular. Okay, that's a 90-degree angle right there. This is a normal. Okay, this is the incoming ray, and this is the angle of incidence. The angle, theta I, is the angle, what's called the angle of incidence. Because this is the incident ray. It's the one coming in. Incident ray. Okay. There's two kinds of rays. Now we talked about the ray of my dog is eating something. I don't have a clue what he's eating. It's okay. It's all right. There's two kinds of rays that now we know about. What is he eating? Oh well, looks like a shoe. Okay. The ray was coming in. Now we know about the reflected ray. There will be a reflected ray. The reflected ray, where this angle of reflection is equal to the angle of incidence. Okay? So a certain amount of is going to be reflected, and we're going to have what we call a refracted ray. This is what we call, this is the reflected ray, and this ray is called the refracted ray. Very similar name, but okay? And you've probably heard the term reflect, refract, okay? Very different, but in the ray will actually, a ray will actually be bent into the glass. So in other words, if this ray were going to go straight, it would come out like this, but it doesn't. You would think, oh, the ray will go straight through the glass, but it doesn't. It bends. And so why does it bend? Well, we'll talk about that. But this is called the refracted